Okay, last time we find that for potential for a moving charge, moving and accelerating charge, then we calculated the field strength tensor, and we write that the electric field, if the charge from electric field from a charge moving and accelerated. So this piece of the electric field is due to the acceleration of charge. So n cross n minus beta cross beta dot divided by 1 minus beta dot n cube over r. So then last time we said that if the speed is low and if there is an acceleration, then we can write the electric field of the accelerated field as E over c. So beta is low, and that will be n cross beta dot divided by r, and this is evaluated at retarded time. And then we look the definition of the power emitted per Solid angle, that is r square s dot n is the Poynting vector. We don't have a 1 over 2 because the fields are not oscillating. So for the electromagnetic waves, in order to take the time average, we are putting here 1 over 2 factor. And we said that the Poynting vector is c over 4 pi e cross b, and b is n cross e. So, and e is the accelerated electric field of the accelerated charge. So that is equal to c over 4 pi square amplitude square of the electric field along n. N is the propagation direction. And then we take this information and we take the square of this. We said that n cross beta, so beta dot is the arbitrary acceleration, and n is our point of interest, making it theta. N cross beta dot is, so if you take the magnitude square of this, you will have b dot square sine square theta. Then the total power emitted per Solid angle could be written as E square over 4 pi c cube square of the acceleration sine square theta. So that means that if there's the acceleration, the fields are dipole fields. So along the direction of the acceleration, no field, but the field is maximum at 90 degrees. This situation will be changed if this is accelerating relativistically. And if you integrate this through all Solid angles, you can find that the total emitted power, and that was equal to 2 over 3 e square over c cube b dot square. This is called the Larmor formula. That represents the total power from the accelerated charge. So what we have done last time, so we said that multiply this by m squared divided by m squared, mass of the accelerated charge, and that could be written as dp over dt dot dp over dt. Okay, for non-relativistically. So this is nothing but the applied force on the charge in order to accelerate, and that is the total power is related with the square of the applied force. So this is non-relativistic Larmor formula. So in order to study what is going on in the relativistic form, there is one invariant form, Lorentz invariant form. That invariant form could be written as a general form of the dp over d tau in 4 as a 4-vector scalar product by itself. So the relativistic form of this, the general form of this, could be written in the following form: 2 over 3 e square over c cube m square dp mu over d tau dp mu over d tau. So this is a Lorentz invariant form because there is a scalar product of 4 vector, and this is the general form. So there's a minus sign, then you can get the positive result, value of the result. So this is the general form of the emitted power in the relativistic form, and today we will look at what is this. So we will be busy with calculating the relativistic form of the total emitted power in the form of Lorentz invariant form, because we have 4 vector and 4 vector, that is scalar product. So all of them are constants there. So let us start to do our calculation. So today, all the course we will calculate and we will investigate what this formula is telling us. So we can, at the moment, maybe keep this. This is the Larmor formula, and this is the relativistic general formula. So let us try to evaluate dp mu, dp mu, dp mu d tau, dp mu d tau scalar product. So the open form is the following: dp mu d tau dp mu d tau could be written as, with minus sign, dp over d tau absolute square minus 1 over c square dE over d tau square. So if you multiply with the minus, you will get the correct definition of the scalar product. And here the energy is gamma mc square, momentum is gamma mv, and d tau is dt over gamma. So basically we will play with this, we will plug in there, and we will try to find the general form of the total emitted radiation if the charged particle is moving relativistically. So let us start to the calculations. This is equal to, so let us plug this information to here. That is equal to what? D tau is dt over gamma. Gamma goes up. Then we have gamma d gamma mv over dt square. This is the first term, minus 1 over c square. D tau is dt over gamma, but square will bring away another gamma square up, and so Then here mc square, square of this, that is m square c to the 4, that is not equal to c square, and we will have what? D gamma over d tau dt square. Okay, so we have gamma square up c square m square c to the 4. So let us try to continue the calculations. So take the m square outside the big parentheses, and here if you take the derivatives you will have what? Gamma d gamma dt times velocity, derivative of the first one, and then derivative of the second one. Gamma times gamma is gamma square dv over dt. Then we should take the absolute square of this minus gamma square c square d gamma dt square. So let me continue. So these are all m square parentheses. So let us continue. M square in the larger parentheses, and take the square of this gamma square d gamma over dt square, square of the first term. V dot v is v square, and the square of the second term is gamma to the 4. This is v dot, and that will be v dot square. V dot square, this is the second term, and the 2 times the dot product of these 2 will be 2 gamma cube d gamma over dt, and d gamma cube d gamma over dt, and we have v dot product v dot product v dot, this is the second term, minus gamma square c square d gamma over dt square. So I am sorry that I am not quite happy to do this in the blackboard, but I want to show to do some simple tricks in the derivations, and then I will discuss the results. So we will do some more algebra, and then we will get the full result quickly. So let us continue from here. So what we can do, m square is there, and take the d gamma over dt square parentheses, this term and that term, that will be d gamma over dt square. In this parenthesis we have gamma square v square minus gamma square c square for the other term. Then what else we have? Gamma to the 4 v dot square, and left over plus 2 gamma cube d gamma over dt v dot. So this piece there, the other piece there, gamma to the 4 v dot square is there, plus 2 gamma cube d gamma over dt v dot is there. Okay. So let us continue. what I needed as a tool, derivatives of the d gamma over dt. So let me introduce somewhere here what is d gamma over dt. Maybe here I can introduce what is this. So you know the gamma is the Lorentz factor 1 over square root of 1 minus v square over c square. Therefore d gamma over dt is what? Derivative of the v with respect to the t. That will be what? From the square there is a 2 minus and minus from the exponent, that makes plus. So exponent is 1 over 2 and the v over c square 1 minus v square over c square. So lower the index by 1, that will be minus 3 over 2, and the interior derivative is v dot. So that should be v dot. So derivative, interior derivative, and the lower the exponent 2 and 2 cancel out and the sign is positive. So d gamma over dt, so you have to keep this calculation, so you will use this later in other calculations. So that is equal to what? This will be cancelled, and this is gamma cube over c square v dot. So this is an important thing for our calculations. Now that means that we have a m square d gamma over dt square of this term, gamma cube c square v dot square. This is the square of that, square of this term, in the parentheses of gamma square c square, in the parentheses of gamma square c square. So you have gamma square, that will be but v square over c square minus 1. So gamma square c square parenthesis is there. So the other term in here, gamma to the 4 v dot square plus 2 gamma cube, this term, and d gamma over dt there, that is gamma cube over c square v dot v. Is it so? Yes, d gamma over dt is this, multiplied by v dot v dot. So d gamma over dt, this is this term, and the other term is there. I think it's okay. So you know that 1 v square over c square minus 1, that is nothing but minus 1 over gamma square from here. So this gamma square will be cancelled, and that will be with minus sign. So altogether, this is equal to the following: m square minus gamma to the 6 c square over c to the 4, again c square, v dot square, this whole term. The next to it, gamma to the 4 v dot square, and the other 2 gamma to the 6 over c square v dot square. So as you see that this term is the same of this term, and that makes plus. So we are coming to the end, and we will study the physical discussions So this is equal to, so now try to write the, we don't need this term, try to write that the total power that was equal to minus 2 over 3 e square m square c cube dp mu over d tau dp mu over d tau. So if you multiply this whole stuff, minus 2 over 3 e square m square over c cube, m squares will be cancelled, and you will obtain the following. So this was the minus of this, okay? So we are calculating, this is the minus of this. You don't have to be multiplied one more minus, because there's a minus here and it is that term. So multiply 2 over 3 e square m square over c cube, m squares will be cancelled out, and you will obtain 2 over 3 is plus e square over c cube, m square over m square, that will be cancelled out. And the leftover terms will be what? This and this term are the same. Gamma to the 6 over c square v dot square gamma to the 4 v dot square. Now we can get the result quickly. Then compare with the non-relativistic case, then we will compare with the linear acceleration and circular acceleration. So we will learn very useful tools. Total power, this is the total power. Distribute the c square inside, this becomes beta, and beta dot, that becomes beta dot square. So that will be 2 over 3 e square over c. Distribute the c square here, this will be beta, beta dot, and beta dot there. So left over is the 1 over c, and take the gamma to the 6 parentheses, then you will obtain beta dot square beta dot square over gamma square we will obtain. This is the total power for relativistically accelerated charge particle. Now you can write this result in a different, very simple format. 2 over 3 e square over c gamma to the 6. Then you have what? Beta dot square plus 1 over gamma square. Where is the gamma? Gamma is here. And 1 over gamma square is nothing but 1 minus v square over c square. Basically, that is nothing but 1 minus beta square. This is 1 over gamma square. 1 over gamma square is 1 minus beta square. And next to it, you have beta dot square, or beta dot magnitude square. So you can write this expression in the following form. So take the beta dot square here. This term comes to here. And say minus this beta square, beta dot square. Let us say beta square, beta dot square, these two with minus, plus this means that this have to be minus, because minus minus is plus. Beta dot beta square. Okay, so what I did, I write here beta dot square, I write here beta square, beta dot square with minus, and I take this term here. So basically this is nothing but beta square, beta dot square, cosine square theta. That is the angle between beta and beta dot. And if you take the parentheses of beta dot square, that will be 1 minus cosine square. This will be, what will be beta dot square 1 minus cosine square theta. That means that this is sine square theta, and beta square, beta dot square, sine square theta is nothing but the square of the beta cross beta dot. Beta cross beta dot. So basically, the total emitted power for the relativistically moving charged particle is in the following. P is 2 over 3 E square over C gamma to the 6, that term, and the rest of them beta dot square minus beta cross beta dot. So this cross product is important, we will see in a moment. So this is called the linear result. In 1898, this is suggested, proposed total emitted power for relativistic accelerated charge particle. What is done? Larmor's results is dp over dt dot dp over dt, force dot force, is generalized to the dp mu over d tau, dp mu over d tau in the invariant form, which is there, and this result is obtained. So what are the consequences of this result? If you go to the non-relativistic case, beta goes to 0, and when beta goes to 0, gamma goes to 1. When beta goes to 0, gamma goes to 1. That is the non-relativistic case. Non-relativistic case. So this term drops, this term goes to 1, and you can obtain the 2 over 3 E square over C beta dot square, or 2 over 3 E square C cube times V dot square, the acceleration square. This is the Larmor result. So that means that this is working well in the non-relativistic case. Okay, this is relativistic, but if you take the non-relativistic case, it is working well. Now, if you want to, so basically, the results are related here. So the Larmor results, we said that it could be written as what? 2 over 3 E square C cube M square and dP over dt dot dP over dt. This is the applied power, applied force, and the power is related with the square of the applied force. Now, basically, there are two important cases. You can accelerate the charge by applying a force, linear or circular. Or in nature, the charge could be circularly moved in the magnetic field. If there's a uniform magnetic field, the charged particle gyrates around the magnetic field. Emission is called cyclotron if it is relativistic. So sometimes you can have B cross B dot terms, sometimes you don't have. So let us investigate the linear results, total emitted power in different limits for a linearly accelerated charge and circularly accelerated charge. So I erase an important piece here. Okay, I can write it later. So if you have a linear acceleration, if you have a linear acceleration, the situation is the following. Beta cross beta dot is 0. Okay? Beta cross beta dot is 0 for the linear acceleration. Acceleration and the velocity are parallel to each other, and the linear result takes the form of 2 over 3 e square over c gamma to the 6 beta dot square. So as you see that if gamma high, powers are high at the order of gamma to the 6. If the gamma is 10, then 10 to the 6 of 10 is a huge number. But this is the form of the linear acceleration. So beta and beta dot, in that case, beta and beta dot are parallel to each other. You can ignore the other term. If you have a circular acceleration, circular acceleration, then beta cross beta dot is not equal to 0. Beta cross beta dot is equal to beta times beta dot, sine 90 degrees. Then the power becomes the following: 2 over c e square over c gamma to the 6 beta dot square minus beta square beta dot square. If you take the parentheses of beta dot square, and that you will have 1 minus beta square. You will have 1 minus beta square, and 1 minus beta square is 1 over gamma square. 1 minus beta square is 1 over gamma square. That means that the power seems to be reduced by a factor of 2 if there is a constant acceleration. But this is a little bit misleading. So that is, this is 1 over gamma square, this is gamma to the 6, and you will obtain gamma to the 4 beta dot square. Okay? So if you compare the circular acceleration, power emitted in the circular acceleration, and the linear acceleration, it seems to be this is gamma to the 6, this is gamma to the 4. So that means that the power seems to be less emitted in circular acceleration. But actually, the physical thing to look at the problem, not in the constant acceleration, under the constant force. You apply force to the charge to accelerate, like in CERN, somewhere. Then let us look at how the powers are related to each other. Okay, here we fix the accelerations. Acceleration here, acceleration here. If the accelerations are the same, the total power in the linear acceleration is higher, gamma to the 6. In the circular one is gamma to the 4. Okay. So if you go to if you investigate the situation, not in the constant acceleration, if we investigate the process in the applied constant force, what will happen? Let us apply a constant force for the linear and circular and see which one is emitting more power. Okay? So if there's a constant force, let's say applied to accelerate the charge, we have to be careful. We have to be carefully evaluate the force. So the force dp over dt will be what? d over dt gamma mv, and this is equal to derivative of the gamma with respect to the t times mv plus gamma m v dot acceleration. So I take the derivative. Okay? I'm trying to calculate the force for the relativistic, the moving charge particle. So I know that the d gamma over dt, take the m parenthesis, d gamma over dt is gamma cube over c square v dot. I calculated this. I am not calculating again. And multiplied by v, this v. And if you take the m parenthesis, this is nothing but gamma v dot. This is the general force for a relativistic moving particle. And for if you have the linear case, linear acceleration, if there's a linear acceleration, then one thing, you know that the v and v dot parallel to each other. Then you can write this v times v dot, and everything is in one dimensional. So that is nothing but v dot is the acceleration. Take the m times the acceleration parenthesis. You can obtain what? Gamma cube over c square. What is left? V. This is nothing but v and v. And there's the v, so they are one dimension. So they are. We don't need a vector sign here. So this, if you take the v dot parenthesis, this is v square, and that is gamma. And go one more step. Mass times acceleration. Take the gamma parenthesis. We have the gamma here. This will be gamma square, v square over c square plus 1. And this is equal to gamma mass times acceleration. Gamma square is 1 over 1 minus beta square. V over c square is beta square plus 1. So basically, if you multiply right of the term 1 minus beta squares will be cancelled, and this will be what? Gamma mass times acceleration, beta square 1 minus beta square divided by 1 minus beta square. This will be cancelled. And this is 1 over 1 minus beta square. 1 over 1 minus beta square is gamma square. So basically, this will be gamma cube, because this is gamma square. Gamma cube mass times acceleration for the linear acceleration. Okay. Now, for the linear acceleration, then we have what? Look at the total power here and try to write this in terms of force. So we have 2 over 3 e square c over gamma to the 6 beta dot square. So basically, this is nothing but the following. So if you take the total power for the linear acceleration, this is the total power. This is equal to 2 over 3 e square c cube, this because beta dot square, gamma to the 6 beta dot is the a square acceleration square for the linear case. So these are the same. Nothing. Instead of beta dot, I write acceleration over c square. Okay. And if you look at here, we have gamma cube mass times a. So that means that this is nothing but dp over dt for linear acceleration. This is the force for the linear acceleration. If you want to write that the total power in terms of force for the linear acceleration, what will be the situation? We have what? Gamma to the 6 a square and multiply by mass square, divide by to the mass square, and this whole term is equal to what? M square gamma to the 6a square is equal to what? Square of the dp over dt. Yes. So this term is equal to 2 over 3 e square c cube over m square dp over dt square for linear acceleration. Okay, so total power, if we apply a constant force, is related this stuff times the square of the applied force. And we are seeing that if you think about the electron and proton, if you apply the same force, which one will be emit more power? Electron, because the mass that is inversely square proportional to mass square. Now let us look at the circular case. Circular total power for the circular case is this. So this is the circular total power for the circular acceleration is this. And so I am erasing the study for the linear case. I concluded what is this. That is the total emitted power if we apply a force linearly. If you look at for the circular case, you can see automatically for the circular case, V and V dot will be 0 for the circular case. V dot, V, okay, so V is orthogonal to the V dot. Therefore, this term drops, so the force, relativistic force on the particle which is moving uniformly circular, this term will be 0, that will be m gamma v dot or m gamma acceleration. So I told you that this is the total power. This is the total power for the circular case, and so this is equal to 2 over 3 e square c cube multiply by m square divided by m square gamma to the 4 square of acceleration. So beta dot square brings us c square, this makes c cube, multiply by m square m cube, and you obtain this. And this is equal to what? 2 over 3 e square over c cube m square. So leave the one of the gamma squares and keep the other one. You will obtain m square gamma square a square. So let me tell you again, 2 over 3 e square over c cube, 1 over m square here. So keep the gamma square there and take this piece. So what is this? M square, gamma square, a square, and what is this? What is this piece? Look at there. Square of the force. So basically, if you make a relation here, this term is the same in the linear case. We have a gamma square here, and this gamma square is very important. So the total power for the circular one, if you apply a constant force, will be gamma square times 2 over 3 e square over c cube m square. So this was the linear case, and that will be dp over dt square. Okay, and what is this? power of the linear. This is very important. So what does it tell? If you accelerate a charged particle applying a constant force, linear and circular, the emitted power is increased a gamma square in the circular one. That is the reason in the accelerators, like in the CERN, the radiuses are huge. They try to make the piecewise linear acceleration, actually. So if you choose the radius is small, there will be loss of power loss. So this power loss will be increased with the gamma square. If gamma is 10, that will be 100. Okay, so basically the relation between circular and linear acceleration, emitted power for the circular and linear is gamma square. We can see this radiating systems. For example, if the charged particle, high energy charged particle, let's say electron, enters the medium of the charges, okay, then it makes lots of Coulomb scatterings. So in each piece, it has curvature. You can find the curvature of radius. That means that the most of the radiation emitted with the curvature motion of the charged particle. In the cyclotron radiation also, if you put the charged particle into the uniform magnetic field, it will gyrate, and the most of the radiation is due to the curvature, circulation, okay? So if it is relativistic, cyclotron is the relativistic definition of the cyclotron is relativistic. So basically, this is an important result. Circular emission, total emitted power in the circular acceleration is greater than by a factor of gamma square relative to the linear acceleration. This is the conclusion of the lecture for today. And we have seen that the relativistic general form of the radiation converted to the non-relativistic Larmor formula. When we choose the beta, V over C is small and gamma as 1, we can get the non-relativistic result. Next time, I will study the radiation pattern of the relativistically accelerated charged particle. I will have two cases, we will have two cases, one for the linear, the other for the circular. So far, for the non-relativistically accelerating charged particle, I said that it is a dipole pattern. But if it is relativistically accelerate, we will see that this dipole will be collapsed ahead of time, and it will radiate in the forward direction with an angle is related with the 1 over gamma. So we will see this in the next time. Okay, this is all for today.